Welcome back. In this video, we are going to solve example 2.1 that is taken from chapter number 2, Strain, and the book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the slender rod shown in figure 2.4 is subjected to increase of temperature along its axis, which creates a normal strain in the rod of epsilon z is 14 to 10 raised to power minus 3 z power 1 over 2, where z is measured in meter. Determine the displacement of and b of the rod due to temperature increase and the average normal stress in the rod. So you can see this is rod AB, which is subjected to increase in temperature, and due to this increase in temperature, the strain in this rod is this one, clear, which I have written over here. So you have to find the displacement of and B, how much it displays downward, and in part B the average normal strain in the rod. So let's start with the solution. So as you can see that Z is measured along the Z axis, that this is your Z axis, clear. So what we will do is that we will take a small portion. This is the small portion which is taken as dz, and it is located at a distance of z from this top A. So if I draw this small portion of z over here, let me draw it. Let this is the small portion, this is small portion which is dz. Okay, now you can see due to increase in temperature there will be a change in length of this small portion dz. So let this total change will be equal to, or this new length will be equal to dz dash, and we know that strain is equal to change in length divided by original length. So change in length will be equal to change in length will be equal to this strain times original length, and original length is dz. So this will be change in length. This is the change in length. Okay, now since the normal strain is reported at each point along the rod, a differential segment dz is located. This is differential segment dz, which is located at a distance of d. So what we will do is that we will find this total length, a new length of this dz, which is subjected to change in temperature. So this dz I can write as dz dash will be equal to this dz plus this change in length. So what we can write it as dz, and this change in length we found that this is epsilon time dz. Since it is acting along z direction, so we can write is that this is epsilon z. So this will be the new length of this small segment dz. Now what we will do is that since this is a rod and this is small differential area, so if you want to find the total change in length, so we will integrate it. So integrate it in both sides. Integrate it on both sides to get the total change in the length of the rod. So what we will do is that we will integrate dz dash, and this will be integral of dz plus epsilon z into dz, clear, and that will be integration from 0 to 200 millimeter, or you can see the total length is 200 millimeter. So 200 millimeter will be equal to 0.2 meter, because we have been given that z is measured in meter. So I will write 0 to 0.2 meter here as well. Okay, so when you integrate it again, you will get here z dash, and that will be from 0 to 0.2. Okay, as we are going to find out the total increase in the length, so I will not integrate it to the left side, only we will integrate to the right side. Okay, so this will be integral of dz 0 to 0.2 meter plus epsilon z times integral of 0 to 0.2 meter into dz. Okay. Now this will give us z, and that will be equal to 0 to 0.2. Since you can see epsilon z is also a function of z, so I will also take it take it to the inner side of the integral. That will be epsilon z into dz 0 to 0.2. So that will give us, this will give us 0.2 plus integral of epsilon z is 40 multiplied by 10 raised to power minus 3 into z power 1 over 2 into dz. And if you further simplify it, it will be 0.2 plus 40 into 10 raised to power minus 3 integral of z power 1 over 2 into dz. So z dash will be equal to 0.2 plus 40 into 10 raised to power minus 3, and integral of z power 1 over 2 will give us z 1 over 2 plus 1 divide by 1 over 2 plus 1. So that will give us 0.2 plus 40 into 10 raised to power minus 3, and that z power 3 over 2 divided by 3 over 2. And if you further simplify, it will be 0.2 plus 40 into 10 raised to power minus 3 multiplied by 2 over 3 into z power 3 over 2. And you have limit as well, 0 to z is from 0 to 0.2. So I will put the limit over here, 0 to 0.2. Okay. Now if you further simplify it, z dash will be equal to 0.2 plus 40 into 10 raised to power minus 3 multiplied by 2 by 3 into z will be equal to z power 2 over 3. So 0.2 power 3 over 2 minus 0 power 3 over 2. And when you calculate it by using your calculator, you will find z dash will be equal to 0.20239 meter. So this will be the new length of this total rod when subjected to increase in temperature. As we are given, we have been asked to find the displacement of point D. So we will find this displacement, which is equal to delta B will be equal to original length, which is 200 millimeter. Clear? That is 200 millimeter or 0.2 millimeter. So change in length will be equal to final length. Final length is 0.20239 minus original length, which is 0.200 meter. So you will see that you will get 0.00239 meter. This is the displacement of point B, and that in millimeter it will be 2.39 millimeter, and this displacement will be downward. So this is the displacement of point B of the rod. Now in our next part we will solve for the normal strain in the rod. So as we know that average normal strain in the rod is equal to change in length divided by change in length divided by original length. So put the value what was change in length. So change in length was this one. You can see delta B, which is 2.39. So 2.39 millimeter. Clear? Divide by original length is 200 millimeter. So when you solve this, you will get the average normal strain comes out to be 0.119 millimeter per millimeter, or this strain is dimensionless quantity. So this is the answer of our this question. Again, if you see that From this equation, which I will write it over here, epsilon z is equal to 40 into 10 raised to power minus 3 z power 1 over 2. And if you put the value of z in this equation, so 40 into 10 raised to power minus 3, z is in meter, so 0.2 power 1 over 2. So that will give you strain in z direction of the rod. That will be equal to 0.118 meter or millimeter per meter again. So you can see both the values are very closer to each other. So that was all about this problem example 2.1. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Although I am not feeling well, you can see from my voice as well as from my handwriting, but I have solved it for one of my viewer or subscriber who requested to solve or explain this example 2.1. Thank you. In this video, we are going to solve example 2.2 that is taken from chapter number 2 strain, and book name is Mechanics of Material by R.C. Hibbeler, and its 9th edition. So statement is when force P is applied to rigid lever arm ABC in figure 2.5a. So this is the figure. The arm rotates counterclockwise about pin A through an angle of 0.05 degree. Determine the normal strain developed in wire BD. So you can see this is the figure. This is rigid arm ABC, and this is supported at point A by using pin support. And this rigid arm can rotate counterclockwise through an angle of 0.05 degree by the action of this force. Clear? So you can see that this wire will stretch when this rotates through this 0.05 degree. So what will be the change in length? This will be the change in length. So you have to find the normal strain developed in wire BD. I have shown this in the figure that due to this load P, this arm can rotate. This was the initial, and now it's rotate through an angle of 0.05 degree. So you have to determine the strain in this wire BD. So let's start with the solution. First step is that let this angle is alpha and this total angle is equal to phi. So we'll find this alpha by using the formula tangent of alpha is equal to, for right angle triangle, that is over here, you can see this is 400 and this is 300, and this is at right angle to each other. So by using this tangent of alpha, which will be perpendicular over base, so perpendicular is 400 millimeter and base is 300 millimeter. So we will get alpha is equal to tan inverse 400 divided by 300. And when you solve this, you will get alpha will be equal to 53.1301 degree. Okay. Now we'll find this phi. So I will write it that this phi will be equal to, you can see this is the total phi. This is phi. So this phi will be equal to 90 degree minus this alpha will give you this portion. This will be 90 minus alpha plus 0.05 degree will give you this phi. So I can write it, this phi is equal to 90 degree minus alpha plus 0.05 degree. So put the value of alpha, so 90 degree minus 53.1301 degree plus 0.05 degree. So we will get this alpha phi angle comes out to be 36.92 degree. Now you have this phi angle which is 36.92 degree. So what we will do is that we will use Pythagoras theorem. Let this length is, this is point A, this is D. Clear? So we will find this length of AD. Again, I will show you this is AD. This is the base perpendicular, and this is the base for this alpha angle. So by using Pythagoras theorem, we will find this length AD. So I will write it by Pythagoras theorem. Length of AD will be equal to under the root 400 square plus 300 square. And when you solve this, you will get length of AD will be equal to, it will be 500 millimeter. Now you have this LAD. So what we will do is that we will take this triangle. You can see this triangle, this one. So in order to find this total length of this portion. Clear? This is length of B dash D dash. Okay. Now what we will do is that you have this. So by using take triangle A dash, sorry, not A dash, B dash, B dash D, and use law of cosine to find B dash D dash, B dash D, or length of B dash D. So I will write it. How you will find this? You can see this is phi angle. So angle opposite to this is this LB dash. This point is B dash. Clear? So we'll find this length by using Pythagoras. By using law of cosine, which states that this length of B dash D will be equal to this length AB dash square plus length of AD square minus 2 times length of AB dash into length of AD into cos of angle between them, which is phi. Clear? And you will take the square root, under root. Okay. Now put the value. You will get length of B dash D will be equal to 500 square plus AD was length of AD was 500 square 500 square, length of A dash B dash AB dash is 400. So I will write it 400 square minus 2 times 500 multiplied by 400 into cos of phi, which is 36.92 degree, and there is a square root or under the root. Now when you solve this, you will get this length of B dash D will be equal to 300.3491 millimeter. So this will be the new length. This will be the length of this wire. So what we will do is that we will now find the normal strain. So let move toward normal strain. So normal strain, we know that this is in wire BD. So we can write normal strain in BD will be equal to change in length of BD divided by original length BD. And this change in length is final length, which is LB dash D minus original length, which is LBD divided by LBD. So final length is, our new length was 300.3491 minus original length. You can check it here. This is 300 millimeter. So minus 300 divided by this 300 will give you the strain in wire BD, which comes out to be 0.00116 millimeter per millimeter, or it will be a dimensionless quantity. Okay, so this is the answer of our this question. Now we will solve this problem by using another method, which is very easy and you will find it interesting as well. So what we will do is that the since the strain is very small, you can see from this the strain is very small. So this result can be obtained by approximating the elongation of wire BD as delta LBD. So we can write this. Let me zoom it. This length is delta LBD, change in length of BD. Okay, so we can find this by using approximation. So you can see this is the delta LBD, this length is 400 and this theta is 0.05 degree. So by using S is equal to R theta, we can also find the change in length. Okay, so I will write it. This change in length of BD will be equal to theta into LAB. Okay, you can see here that this is LBD, this is theta, and this is, so S is equal to R theta. So S is delta LBD, R is 400, clear, and theta is 0.05 degree. So what I will write is that this degree is 0.05 degree multiplied by this LAB is 400 millimeter. Now we know that 2 pi radian is equal to 360 degree. So 1 degree is equal to 2 pi radian over 360 degree. Okay, 360. Okay, so we can write 1 degree is equal to pi over 180 radian. So we'll convert this 0.05 degree into radian to get this delta LBD. So 0.05 multiplied by pi divided by 180 radian multiplied by 400 millimeter, and when you calculate it you will get this change in length of BD will be equal to 0.3491 millimeter. Okay, now you have this change in length. Again you can use this formula that strain in BD is equal to change in length of BD divided by original length. So put the value 0.3491 divided by 300 will give us 0.00116, and unit will be millimeter per millimeter, or it will be a dimensionless quantity. So again you can see both will give you the same result because this strain is very small. So by this way we can solve this problem in two different ways, and I have shown you. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.